This is part 4 of the review for chemistry for the final exam. We previously took a look at a highly mathematical chapter, which was chapter 10, and the concepts you'll need to know is molecity, going from grams to liters or liters to particles or grams to particles, etc. Also calculating the percent composition by calculating the molar mass of the substance by adding the sum of the atomic masses, and then calculating the percent by taking the part divided by the whole and multiplying by 100. Okay, so these are two highly mathematical types of problems. Looking at chapter 12, another one is going to be mathematical. It's a grams, moles, moles to grams. This is going to be a basic one. There's going to be no limiting reactants on this test. So it's just basically, do you know how to convert grams, moles, moles to grams? So we're going to go ahead and get started. And we are going to be converting 64 grams of methane. So we have 64 grams of CH4. Let's use this formula up here. We have CH4, we actually have 2 oxygens that are required to burn 1 methane, and it produces 2 H2Os. We'll need that because we'll need that for the molar ratio for this problem. We want to convert from the methane to water. So if I have 64 grams of methane, how many grams of water will I get from this equation? So it's a grams, moles, moles to grams. So it's going to require 3 steps to do this. So here's 1, 2, and 3. So see if you can do this. We've already used the, I think we've calculated the molar mass for this, but go ahead and use the value up here. But you also need to calculate the molar mass for water as well. Take a minute and see if you can answer this question, and then come back and we'll see if you're right. So please pause now. Okay, hopefully you paused, and we're going to be checking this now. We want to cancel my grams of CH4 and convert to moles of CH4. So we're going from grams to moles using the molar mass. 1 mole of CH4, we've already calculated this earlier, is going to be 16.0 grams. So the grams of CH4 cancel with the grams of CH4. So now I need to cancel the moles of CH4. Moles of CH4, and I want to convert to what I'm going into, which is the water, moles of H2O. For this, again, I need the molar ratio, which are the coefficients. So in front of the CH4 is a 1, invisibly, and in front of the water is a 2. The moles of CH4 will cancel, and now I have moles of water. So I use the molar ratio, going from moles to moles. Now I need to go from moles to grams. So I'm going to cancel my moles of H2O and convert to grams of H2O using the molar mass. 1 mole of H2O weighs, and for this we can do the list the number of hydrogens and oxygens that I have. So I have 2 hydrogens times a mass of 1.0. I have 1 oxygen times a mass of 16.0. That gives me 2.0 and 16.0, and water will weigh 18.0 grams. So the oxygen weighs 16, each hydrogen weighs 1, 16, 17, 18 grams for that. The moles of H2O cancel, and you should get 144 grams of H2O. So typical grams, moles to grams of a substance. Next one is mathematical as well, and it's calculating the percent yield. And again, the formula for percent yield is what did you get in your experiment divided by what you're expected to get. So let's say we started off with 64 grams of methane. We would expect to get 144. Okay, that's the expected. Let's say our experiment actually produced 131 grams of H2O. What's my percent yield? Well, what I produce is what I got. So I got 131 grams. divided by, we were expecting to get this based upon my 64 grams, 144 grams. We multiply this by 100%. If you do that on your calculator, you can double check this. This comes out to be 91.0%. That is it for all the mathematical problems that are going to be on the test, so make sure that you are aware of all of these. Okay, so we've got 1, 2, definitely 3, 4, and a conversion problem, 5. These are related to the conversion problems, probably a percent error, 6. This, I think, is a multiple choice problem as well. And then don't forget there's going to be some type of density problem. Okay, so let's continue on to chapter 13. How kinetic energy, and remember kinetic energy is the energy of motion. We defined kinetic energy as a symbol of Ke. In physics, it's just the symbol K. But kinetic energy is the energy of motion. How does motion, the kinetic energy, affect the collision of particles and the pressure of a gas? So if you think of a pressure cooker, okay, you put it on the stove and you seal it. You're trying to cook a lobster, for example. Okay, you increase the temperature of the pan because you're put the stove on. What's going to happen is you're going to be increasing the kinetic energy of all the particles on the inside, so all the water particles that you're steaming with the lobster. So if you're increasing the kinetic energy, you're increasing the motion, you're increasing the speed. And if you're increasing the speed of these particles, these now they're gaseous particles that are just going around on the inside of the pan, you're going to increase the collisions. If you remember, we discussed if we blindfolded you and you were running around the room and counting the number of times you hit somebody, the faster you go, the more collisions that you're going to have. This is going to be increasing the force on the container, or the force on the cooker, on the side walls. They're going to be hitting these. And there's this formula for pressure. Pressure is equal to force over area. And if I'm increasing the force, I'm increasing the pressure. So the net effect of increasing the temperature is to increase the pressure inside of a pressure cooker. And that will be able to infuse those gaseous water particles into whatever you're cooking a lot faster. What happens to pressure at higher or lower elevations and why? So at higher elevations, well, this is the sea level and the mountain. Okay, so I'll just draw this really quick. Okay, at sea level, you have much more air pushing down on top of you. So at higher, we'll do the higher here and we'll do the lower here. So at lower elevations, right here, you have more air pushing down on top of you. So that's going to equal higher pressure. You're going to increase the air pressure. At higher elevations, you have less air pushing down on top of you. So you have less air. That's going to decrease or lower your pressure. So pressures at higher altitudes are lower, which makes it difficult to breathe up there. Okay, on to the last page. What happens to kinetic energy at absolute zero? You can go ahead and cross that off because we did not, did we discuss that? I don't know if we discussed that in detail. I'll go ahead and I'll eliminate that problem. Evaporation, condensation, and melting points. So if you are increasing the energy, you're going to have your solid, liquid, and gas. We can also decrease the energy as well. And in between these phases, we have these points. So what exists between a solid and a liquid? If you're increasing energy, so just think of ice. You're going from solid ice to liquid water, you're going to melt it. So you're going through the melting point. Going from a liquid to a gas, you're boiling it. So it's going to be the boiling point. If you're going from water to ice, you're going to freeze it. So it's going to be the freezing point. And the last one is going from a gas to a liquid when things condense, or the condensation point. So we have evaporation is also going to be your boiling point. Condensation we have here. Freezing is going to be the freezing point. Melting point is going to be MP. And the phases that exist between them. So a potential problem could be you're condensing a material and you're decreasing the energy. What two phases do you have between? Or it's going from what phase to what phase? So if you're condensing and we're decreasing the energy, we're going from a gas to a liquid. Okay, here's another one. If you're increasing the energy and you are going from solid to liquid, what point do you have? You have your melting point. So there'll be questions like that. Concept of evaporative cooling. This is like your sweat. Here's your skin. And here's a globule of sweat. Now this is in the liquid form. What happens is this is going to evaporate. So we have evaporative cooling. So the liquid is going to evaporate. So this particle on the surface is going to become a gas. But going from a liquid to gas requires energy. Like a pot of water, you need to add energy to get it to boil. So it needs energy to do so. So the energy is actually pulled from the liquid and is going to cool that liquid. If you remember, I dropped some acetone on your hand and it got very cool. The acetone liquid turned into a gas and it required the energy. It came from the acetone, and then now your skin is actually warmer. Remember, heat goes from hot to cold, so the energy gets pulled from your skin and goes into the liquid droplet. Since the energy is being pulled from your skin, it's going to cool your skin down. What happens to boiling point at higher elevations and why? At higher elevations, on top of a mountain, you decrease the boiling point. This is just like when I put it inside of the vacuum. There's less atmosphere pushing down. You have less of a lid. So you have less of a lid that pushes down, okay, on that. When I mean less of a lid, there is less pressure pushing down. Since there's less pressure pushing down, it's going to be easier to boil. So it's going to be easier to boil, and that will then make a lower boiling point. So the boiling point decreases because we have less pressure pushing down. Why do ionic compounds have higher melting points? This is based upon a lab that we did, one of our first labs, and that is comparing sugar and salt. Sugar melted at a very low temperature. Salt did not. So with salt we have Na plus and Cl minus. We have this electrical attraction between them. So in order to get these ions to start moving, we have to break this electrical attraction that ties them together. So you have to add energy. You have to increase your energy to separate the ions. Okay, that's going to equate to a higher melting point. Crystal versus amorphous. Crystal has a regular 3D pattern. Like a beautiful quartz crystal. Light is able to pass through that because all of your molecules are packed and aligned together. Amorphous means A means without, morph means shape. So there's no crystal pattern. meaning that there's no regular 3D pattern. So it's more randomly organized like this. And light won't pass through that. Okay, all these next ones refer to a phase diagram. Okay, so can you read and interpret a phase diagram? So we can use this space, draw a phase diagram. Pressure is over here, and temperature is on this graph right here. Okay, so let's take a look at a common substance, and let's just say that it goes to here, and it looks something like this. So we have a solid, liquid, and down below here will be a gas. So if you're on the line, like right here, you're between two phases. When you're on the line, you have two phases. If you're on this line right here, you're between a liquid and a gas. If you're here, you're between a solid and a gas. And right here is a very special point, triple point. This is when you have all three phases at the same time. And that can be accomplished with most substances as long as you have the right pressure and temperature. So this occurs right here. That's the triple point. Let's say that this is going to be right here, 80 degrees Celsius. Let's say this is going to be 20 degrees Celsius. So let's also take a look at a few processes. We're going to be starting off at 80, and at, let's say this is sea level, 1 atmosphere of pressure, sea level. And so at 80 degrees and sea level, we're going to be right here. We're going to be in the liquid phase. Then we're going to cool this to 20 degrees at 1 atmosphere. Okay, so we're going to cool. And when we cool something, we go from liquid to solid. And then what we're going to do is we're going to now decrease the pressure. Here's the pressure, higher pressure at 1 atmosphere. We're going to put it in a vacuum. And what's going to happen is this, just like water, is going to begin to boil. It goes from a solid to a gas. Actually, it's not going to boil. It's going to sublime. It's going to remove all of the material. So it's actually not going to boil it. In this case, it's going to be going from solid to gas, and it's going to completely skip that liquid phase. This process of going from solid to gas is sublimation. So when you go from solid to a gas, and there's no liquid phase. Carbon dioxide does this at normal atmospheric pressures. It goes from solid to gas just by increasing the temperature. So it starts off at a solid over here, and then it would go into the gaseous phase. So again, triple point right here, where we have all three phases at the same time at that pressure and temperature. This would be approximately in between 20 and 80. That would be about 50 or 60 degrees for this material. We started at 80 at atmospheric pressure. We cooled it to room temperature at 20 degrees, and then we lowered the temperature, and we got sublimation. So this process right here, if you want to turn this on its side, this is sublimation when you go from a gas, solid to a gas. That concludes our review. Please let me know if you have any questions.